All right, let's get right into it. Today, we're jumping into the driver's seat to really understand the physics behind something you see every single day, the perfect turn. We're talking, of course, about banked curves.
So think about it for a second. When you're driving and you take a highway off-ramp, the curve feels pretty gentle, right? But then you watch a car race on TV, and those curves are so steep they look almost vertical. Why the huge difference? I mean, they're both just curves in a road. What's the deal?
Well, it turns out that massive difference isn't an accident at all. It's all about physics, and it's all about designing the perfect turn for a very specific job. And today, we're going to break down exactly how that works. Okay, so first things first, let's talk about the basic problem engineers are trying to solve here. How do you get something moving really fast, like a car, to stick to the road when it's going around a curve? Now, here's the really cool part. The ultimate goal, the most elegant solution, is to design a curve so perfectly that a car could take the turn even if the road was a sheet of pure ice. The whole idea is to design it so the car doesn't even need the grip from its tires to stay on course. And the tool they use to do this is the banked curve. It's pretty much what it sounds like, you know? The road itself is tilted or banked toward the inside of the turn. And that tilt, well, that's the secret sauce. It uses the force of gravity to help pull the car through the curve, so it doesn't slide out. But how much of a tilt is the right amount? That's not just a guess. Oh no, it is pure math. And it turns out engineers have a kind of blueprint, a core formula that guides every single one of these designs.
What's so amazing is how all these complex physics, we're talking forces, vectors, acceleration, the whole shebang, it all gets boiled down into one surprisingly simple and honestly kind of beautiful equation. This is the key that unlocks the whole thing.
And here it is. The tangent of theta equals v squared over gr. It might look a little intimidating, but it's not, I promise. All this is saying is that the steepness of the bank, that's our theta, is directly related to the car's speed squared, divided by gravity and how tight the turn is. This little thing is the engineer's blueprint.
So let's quickly break that down so it's not just a bunch of letters. Theta, that's our bank angle, how steep the road is. V is simply the car's speed. G is gravity, which is always 9.8 meters per second squared. It's a constant. And R is the radius of the curve. You know, is it a wide sweeping turn or a tight hairpin? These four things are all connected.
Okay, enough theory. Let's actually put this formula to the test with a real-world example. We're going to go back to that gentle highway off-ramp we talked about at the beginning. So for our little case study, let's say we have a pretty normal curve. The radius is 200 meters, that's our R, and we know that the road has a gentle bank angle of 15 degrees. That's our theta. So if you're the engineer, here's the question you need to answer. With this specific angle and this specific radius, what's the perfect speed for a car to take this turn without needing any help from friction? To figure that out, we just take our main formula and shuffle it around a bit to solve for v, the speed. We plug in the numbers we know, gravity, our 200-meter radius, the tangent of 15 degrees, and then we just let the math do its thing. And what pops out? About 23 meters per second. If you convert that, it's roughly 51 miles per hour. So there you have it. That's the official design speed for this curve. Okay, so that makes total sense for a highway. But what happens when speed is the #1 goal, like on a racetrack? Let's see how the math completely changes when the needs are different. On a racetrack, it's a totally different game. It's all about speed. So let's say the target speed for a specific turn is now 30 meters per second, which is about 67 miles per hour. So now the problem is flipped on its head. If we keep the same 200-meter radius turn, but we need cars to safely hit it at a much higher speed, how steep does that bank angle need to be? Well, we use the exact same formula, but this time we solve for theta. We plug in our new, faster speed, and the math tells us we need a bank angle of almost 25 degrees. That's a whole lot steeper than the 15 degrees we had on our highway ramp. So we've just looked at two really different situations, but we used the exact same physics to solve them. So what's the big picture here? What's the main idea we should be taking away from all this? When you put them side by side like this, it becomes crystal clear. On the left, our highway ramp, a 15-degree angle works perfectly for about 23 meters per second. On the right, our racetrack. To handle that higher speed of 30 meters per second, the angle had to jump up to almost 25 degrees. The connection is right there.
This really drives home the fundamental rule here.
The core idea is that as a car's speed goes up, the angle of the bank has to go up too, just to keep things stable. It's a direct relationship, and it's one that engineers have to get exactly right.
So the bottom line is this. The steepness of a curve isn't just for looks, and it's definitely not random. It's a precise calculation. The speed a road is designed for completely dictates the angle of the bank. And this bit of physics is what keeps you safe on the highway and what allows race cars to do those incredible things they do. But this does leave us with one last really interesting question to chew on. Everything we did today was based on a perfect world, a frictionless road. But in reality, we have the grip from our tires. So how does that extra force, that friction, change the equation for the engineers? That's definitely something to think about.